This problem was assigned to Chemistry 1 Advanced students on 2016, September 7th. And the problem states how much heat will be produced from burning 50 grams, 50.0 grams of butane. And I'm going to show you the solution. I'm not going to have you exchange papers today just to make it a little easier for the substitute teacher, but I'm going to show you the solution. If you didn't do the homework, you got off easy. If you did the homework, you're going to check your own work. So, if we have butane, we're going to look on this chart and find that butane is right here. Here is the equation. Here is the heat of combustion produced. This is the heat of combustion change, or given, lost, if you will, by these products when they become, these reactants when they become these products. So one of the things we're going to have to do is write the proper equation that includes heat of combustion, and then we're going to do the calculations. We're going to have to find the molar mass for butane in order to calculate this. So let's start by setting this up, okay? One way to approach this is to start out by putting your starting amount over 1. So let's just say we start with the 50.0 grams of butane. I could write the word butane, but we also could write the formula. This is the formula for butane. It's always the first chemical formula in these combustion equations. It's not always the first formula in every equation, but in a chart like this, that's what we're talking about. The first chemical on the list here, or in the chemical equation, is the name of the chemical in this first column. So butane is C4H10. And we're going to put our starting amount over 1. That's the usual practice in this class. Now, our heat of combustion is listed in kilojoules per mole. Per mole of what? Per mole of the starting chemical, butane. So it's per mole of all of these, okay? In this case, per mole of butane, 2874 is the number of kilojoules of heat produced from burning 1 mole of butane. In order to do the calculations, we have to have butane in moles. So we have to calculate the molar mass. This is mass, and we want the molar mass to find the moles. So we're going to write down the chemical formulas for all the elements, the elemental formulas or symbols for each of the elements in the formula here, and write down then from the periodic table what the atomic mass is. The atomic mass for carbon is 12.0107. The atomic mass for hydrogen is 1.00794. That little superscript right there is not part of the molar mass. That superscript right there is not part of the molar mass. That superscript right there is a reference mark, a citation that draws your attention over here to this small inset table. We don't want to get into that right now. So 1.00794. Now, the definition of molar mass is the sum of all the atomic masses of all the atoms in a formula written in units of grams. We're not going to add carbon 4 times, carbon's mass 4 times, and hydrogen's mass 10 times. We're going to use multiplication to help us speed through some of that addition. So there's 4 carbons and 10 hydrogens. We'll do that math. So 12.0107 times 4, and I get 48.0428. And if I multiply this times 10, I'm just moving the decimal place one place, so I'll just do this the fast way here, okay? 10.0794. Okay, and there actually is a 0 on the end. We won't worry about it because it's going to round off anyway. And we can add these together now. So this number that I've got on the screen plus 10.079 0.94, and we get 58.1222. This number by itself doesn't tell us much. You have to remember that every number you write down has to be related to something, has to be measuring something or calculating something, or you have to tell me what that number applies to. This number is the grams of butane in 1 mole of butane, so we can write an equality statement, 1 mole of butane. And in my classes, when you calculate the molar mass, it's always required that you finish your molar mass calculation by writing out this equality statement. Now we can take this equality statement and build a conversion unit. I have grams of butane on the top. I want grams of butane on the bottom. The left side of the equality statement has the grams of butane. So we're going to write 58.1222 grams of butane on the bottom. On the top, we're going to put 1 mole of C4H10, and this fraction I just built is a conversion unit. Since these two things are equal, this fraction equals 1. When I do the math, we're going to change the way we're measuring this number of grams of butane, but we're not going to change the actual amount, because when you multiply by 1, you get the same thing you started with. Now we're ready to use the molar heat that's produced, the heat of combustion here. Let's write out an equation that includes this heat of combustion. Here's butane, here's the equation. We're going to just write it out down here. So C4H10, and that symbol G is for gas. So that's the physical state. Then we have 13/2 oxygen. Combustion equations are the only equations where you're allowed to use fractional coefficients, because we always want the coefficient in front of the fuel. Butane is our hydrocarbon fuel. We always want the coefficient in front of the fuel to be 1. All other equations, all other chemical equations have to have whole number coefficients. So instead of equals, we need an arrow here. 4 carbon dioxide molecules and 5 water molecules. Now, while we're right here, a couple of things. Every time you burn a hydrocarbon fuel to completion, it's a hydrocarbon fuel because you've got hydrogen and carbon. Every time you burn a hydrocarbon fuel to completion, you have the same products every time: carbon dioxide and water. The coefficients in front will change depending on what your chemical is, what your fuel is. The fuel is butane. But you always produce, when you burn a hydrocarbon fuel, if you burn it to completion, you get carbon dioxide and water. Those are always your products. Now we can add in the heat of combustion. Since we have 1 mole of butane here, and this is the kilojoules per mole produced, and we have 1 mole of butane, this is the amount of energy produced right here from burning 1 mole of butane. So we can put that in the equation. That's a product now. Now, just to remind you, this is a product. This is what's happening in the system. These chemicals reacting are losing this amount of energy as the bonds holding these two chemicals together here are broken up and reforming these bonds. The bonds in these two chemicals here have less energy stored in them than the bonds in these two chemicals. So we're losing energy when we break this up and reform them into this. And so the system is losing energy, and the surroundings, this is the product over here, the surroundings are gaining the same energy. Whatever energy is lost by the system is gained by the surroundings. Okay, so we've got a balanced equation now, and from this we can take these two things in the balanced equation and write a different kind of conversion factor. not a conversion unit, but a conversion factor to go from one chemical species to another species. In this case, the species is energy. So I can put this on the top, and the 1 mole of butane on the bottom. Okay, and I put it that way so that units and species cancel out just as x's and y's in algebra cancel out. So grams can cancel grams, and butane can cancel butane. And moles can cancel moles, and butane can cancel butane again. Okay, so this leaves me with units of kilojoules. That's what I want to find, the heat that's produced. Kilojoules is a measurement, one measurement of heat. Kilojoules actually measures any kind of energy, and heat is a type of energy. So now I'm just ready to do the math. Okay, so we're going to plug this in the calculator now. And we've got 50.0 times 2874. We're going to hit enter. Let me go back to the work I'm actually doing here. I'm multiplying once across the top. I'm hitting equals. Then I'm going to click my divide button, put in this number, and hit equals again. So multiply what's across the top, hit equals, then divide by this number, and hit equals again to get your final answer. So I put in the two top numbers, I've hit equals, now I'm ready to divide by that answer using the bottom number, 58.1222. And I get this number. So here's the number I have. I'm going to look at my problem here, and of the numbers in the problem, there are 3 measured or calculated numbers. This is a measured number. This is a calculated number. We know because we calculated it down here. And this is also a calculated number. These ones are whole numbers. Whole numbers are infinitely significant. We just ignore those for figuring out significant digits. Of our measured and calculated numbers, this one, and this one has the least digits. So we want to have our final answer rounded off to have that same number of digits. Now let me include my units of measurement here. And the first 3 digits are significant then. Everything else is insignificant. And anytime we're rounding off a digit in the ones place, as we are here, we have to write our answer in scientific notation. For scientific notation, your decimal has to be just to the right of the first non-zero digit. So it becomes 2.47. We're going to move the decimal place 1, 2, 3 places. So that's times 10 to the 3rd power kilojoules. And that's the final answer. All right, let's talk about how we would normally go about giving you points for this. Not grading it today, but if we were, everything I wrote down here on this page is worth a point. I'd give a point for this formula, a point for the plus sign, a point for this coefficient, a point for this formula, a point for the arrow here. The arrow is a type of operator, it's required. A point for the coefficient, a point for the formula, a point for the plus sign, coefficient, formula, plus sign, number, unit of measurement. All those would be points. Now, later in the semester, when we get into physical states, I will give points for physical states, like all these gas symbols, these G's here in parentheses. Calculating molar mass, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 points for calculating the molar mass. And you know how I've done these already, okay? So it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so forth. You know how to count those up. So I want you to know that I'm expecting you to do these things, and so I'm giving points for these things, okay? Show me your work. I'm from Missouri.